represent the derivative using finite differences, then we can, first of all, break up the domain and write individual unknowns at each point, right? Boundary points are given by the problem itself. But we don't know these things. We don't know these points. So we want to know the height at this point. So it's like this. We have the domain written here, but height is something like this, right? Height here might be this. Height here might be this, height here might be this, and so, right? So consider a mountain on top of this. Do you follow me? We know the height at boundaries, right? We know the height at boundaries. So some height is here, some height is here. We know the height at the boundaries, but we don't know the height inside. This is the situation. So what should we do to solve the problem? We, first of all, name the unknown. We can name this X, Y, Z, A, B, C, D, E, any way we want, right? X, Y, Z, anything is possible, but it's not organized. So to do it, we may name this way. Oh, let's call this U sub 1, 1. Then we may call this, U sub 2, 1. Right? What is better? 1, 2 might be better because it doesn't matter. Anyway, it's okay. But if we consider row and column, then 1, 2 might be better. But doesn't matter. 1, 3. U sub 2, 1. U sub 2, 2. U sub 2, 3. U sub 3, 1. U sub 3, 2. U sub 3, 3. Any questions? Just naming it. It's not special. If you don't like it, you can name these things using A, B, C, D, E, F, and so on. Anyway, it's possible. But we are naming these things using organized schemes. Why? Because if we somehow name these things using these arrays, then we can program it by just one line instead of A, B, C, D, E, F. All these things are somehow hardwired. Do you follow me? So we are naming these things. Then how can we represent the derivative in the direction x? This is the x direction. This is y direction. And how can you represent the derivative? Usually, derivative is written by, for instance, at this point, derivative is u1, 2 minus 2 times u1, 1. And then for convenience, let's label this the same way. This is not unknown. This is known. But we name this anyway for convenience. So it's called u1, 0. Then plus u1, 0 over this distance h squared. So this is the way to represent the derivative. And y-directional derivative can be written the same way. u 2, 1 minus u1, 1 minus u0, 1 over h squared. So I wrote down uxx, now I wrote down uyy, and the right side is 0. So please browse these things and ask questions. So is this the only way? Is this the only equation? No. We can do the same thing at this point, right? At this point, at this point. So we can do these things at 9 different points, right? We can do the same thing at 9 different points. But if we hardwire unknown names using A, B, C, D, E, F, then each time we should create this kind of relation using the hardwired names, right? It's not convenient. But because we used label, instead of writing down these things 9 different times, we can just automate it using ij. So generic position is uij, right? This is the generic position. Then this position, one advanced position to the right side is uij plus 1, right? And one less position, right? Less advanced position is uij minus 1. Similarly, one advanced position in the y direction is uij plus 1j, and one less advanced position is uij minus 1j. Yes, thank you. Yes, thank you. I'm completely out of mind. Thank you very much. So this is the situation. So if you completely understand, then it's good. If you don't, then please let me know. Then what kind of relation can you get? So this is for a specific one, but specific one is not easy to implement because we should write down these things 9 times, right? So it's not good. So let's use generic relation to write the same thing at this position. So at some generic position, ij related point, we can write the relation this way. 0 equals uij plus 1 minus 2 times uij, and then plus uij minus 1 over h squared plus ui plus 1j minus 2 times uij plus ui minus 1j over h squared. Then take a look. Can you solve this equality? Can you solve this equation for uij? Can you solve this equality for uij? It's possible, right? First of all, we multiply both sides by h squared, then we drop this h squared. And we move this uij to the left side then. 4 times uij equals remaining things. uij plus 1, uij minus 1, ui plus 1j, ui minus 1j. And then we can divide both sides by 4. So we can solve this for uij. So instead of writing down this kind of equality 9 times, if we use ij, then we can loop these things for I running from for I running from 1 to n. In this case, n happened to be 3, right? And then for j running from 1 to n, right? So in this case, it happened to be 3, but in general, we can break up a more refined way and then do those things. And then inside this loop has this portion determining uij. In other words, we are solving this equality. We are solving this equation and then get uij. So this is the crux of the problem. And if you have a question, ask me. If you don't, then I will let you know. What about bookkeeping work to use this method? So the goal is solving this thing, and then solving this thing became solving this thing for these 9 points. Of course, if we find the number of points, then we may have more unknowns, right? But in this case, we focus on 9 unknowns. Then instead of writing down 9 equalities, we write down 9 equalities of this sort, and we are solving this thing using SOR. So using SOR, we write down this thing this way. Right, SOR. Then what is the next thing? Next step is this one. We want to initialize the height. So take a look. I will use the given shape one more time. Initially, boundaries are known. So assume that this height is known. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Right? This height is 15 and this height is 16. Assume the heights are somehow known at the boundary. You follow me? At the boundaries, heights are known. So any boundary point is given, then height is known. Then we want to initialize these heights too. What is the best way to initialize this height? Averaging it. In other words, here is 1, here is 7, then midpoint might be around 4, right? The average of these two values is 4, right? And what about this? 1 and 4, then average of this value is 2.5, right? And average of 4 and 7 is 5.5, right? So we just initialize the numbers. Why? Because in SOR, we should initialize all the unknowns, right? All the unknowns are initialized to do the loop, right? Do you follow me or not? So in SOR, when you apply SOR, we use some initialized vector. So 1, 0, 0, or 1, 1, 1, anything can be used. So same thing. We initialize these things intelligently. How? We just take the average. Average of 1 and 7 is 4, right? Average 1 and 4 is 2.5. Average 4 and 7 is 5.5. Then let's do the same thing. 16 and 8. Then what could be the average? 16 and 8, then it is 24. It is 12, right? What is the average of 12 and 8? 10. What is the average of the 14, right? Similarly, what is the average of 15 and 9? 15 and 9 added to 24, it is 12, right? 12. And what is the average of this 15 and then 12? About 13.5. What about the average of this? 11, 10.5, right? So roughly, we do the initialization using average. This isn't absolutely the unique initialization. This isn't unique initialization. You may initialize differently. When we run SOR, almost any reasonable vector can be used as initial solution vector. So I will return back to the SOR part so that you can remember or review that idea. So take a look. In SOR, as you can see, we use right side, right? Right side xi, x, right? Xi vector to determine new xi, right? So we use these things to determine new xi. So we use these values roughly. We use these 4 values to determine this value, right? So to use these 4 surrounding points, we should have some numbers inside already. Then how do we get these numbers? Initialization. So we initialize these things, and then using our initialization, we determine it. Then let's check this case. Assume that this is the boundary and we are now calculating this using 4 boundary points. Then roughly, if this is the case, then U22 equals, by this surrounding points, 1/4 multiplied by 4 plus 10 plus 12 plus 14, and it should be 26, 30, 40. 40 divided by, so it should be 10, right? This should be 10. Do you follow me? This should be 10. So to use SOR, let's return back. To use SOR, we should have initialized xi's to better the xi, right? So we should have initialized vector to better the value. So please browse the idea and ask questions. So we run these things systematically. We run this for this point. So by 4 surrounding points, we determine it. After determining it, we determine the next point using 4 surrounding numbers and determine it. And then we determine it using 4 surrounding numbers and so on. So we go one pass. After going from this to the end, we return back. And then we calculate this one more time. So we do these things many times. Then each time we may have better result. So we do SOR, meaning we are looping and looping. And once this vector, infinite norm of this vector do not change very much, we may stop. Do you follow me? So this is the idea of solving PDE problems using SOR. Of course, in the course called Scientific Computation, we handle these things extensively. Not just this thing. Many methods are covered. In any case, this is the idea of solving this. So this is the reason why this differential equation problem is asked in systems chapter. Because by solving system like this, we solve PDE problem. So I will pause. You may check whether you completely understand everything from scratch, from just beginning till the end. Check it. Let me know. Any step that you think is too tough for you to handle. Let's go back. So the same thing, right? The same thing. And then we have how many positions? Total 9 points, 9 inner points, right? The same, exactly the same. And boundary can be calculated. Assume that x is like 0. Then the height is what? 1. 0 minus 1 squared is 1. Do you follow me? Assume that x is 1/4. So in this case, I will open it on the right-hand side and then determine values. So take a look. So assume that we want to determine this height, right? We want to determine this height. Then x equals 0 can be used, right? X equals 0. Then 0 plugged in determines this value. So instead of 14, you should write 1. And the next point, 1/4 0, right? 1/4 is plugged in, then 1/4 is plugged in 3/4 squared. So 9/16, right? 9/16 is this number instead of 14, 13 that I artificially used. And so you can determine all these things and exactly the same thing happens. Any other questions? Browse it and check whether you can complete this thing. So from initialization, right, all boundaries are calculated by the boundary condition. And then afterwards, you average these things to determine it. You average these things to determine it, average these things to determine it. Or the other average is okay. I don't mind, right? Average of these things and determine it. Average these things to determine it. So numbers might be different. Doesn't matter. Because we are not stuck to the numbers that we initialize. Because we will really run the loop, right? Then after rotation and rotation, we will get better result each time. And eventually, it will converge it to the solution. Of course, this is not a scientific computation course. I don't want to go too deep inside the differential equation solving. But at least the idea came from the differential equation solving. But after removing these things, it becomes system problem, right? System of 9 unknowns. Right. So what, u of quarter is what? U of half is what? Something like that, right? Nine unknowns. We don't know 9 heights, right? So what is the height at? Right, 9 different heights. That's all right. Yes? Here. It's right here. Here. J, K are between 0 and 4. So how many numbers are there? 1, 2, 3 numbers for I, 1 to 3 numbers for J. Right. Right. Yes. So J and K are between 0 and 4 integers. So evaluate U of 1 quarter. So I named U of 1 quarter using U sub 1, right? So U of 1/2, 1/4 is U sub 1, 2, and so, right? But you may use different approach if you want. So you may even label differently. U1, instead of you call this U1, you may call this U21. Any way you want is okay. In scientific computation, we design these things completely from scratch and solve PDE problems. But this is not a scientific computation course. We are focusing on systems. So after this conversion, we focus on just systems like this, right? Systems like this. We are solving systems with 9 unknowns. Yes? You calculate 9 unknowns, say U11, U12, U13, U21, and so on, and then U33. So this is somehow found, and then these are populated by, for instance, 1.25, 1.11, 1.31, and so on, right? Then this is the first iteration, right? Of course, initialization determines these things like this, right? So initialization will determine these things with some numbers. But after running this, and then you get the next vector after running SOR, then you may get different numbers, right? So you run these things and check the difference between, let's call this xn, and let's call this xn plus 1. So xn minus xn plus 1 as vectors. And then we consider any norm, right? Less than epsilon. So we stop when the difference between the previous result and the next result are, the difference is less than some number that you chose, like 0.0001 or something, then you stop looping. So this is the reason why we studied about norms, right? Norms measure the size. What is the size of the difference? Very small. It means They are close enough. They are close enough. Please browse these things and ask more questions. If you don't like to use vectors of one dimension, then you may use this thing. Oh, I don't like to use that. I like this matrix. So I call solution matrix, and the solution matrix consists of U11, U12, and so on, right? So U33. Do you follow me? Then my solution matrix is this, and this is Xn, and somehow this is filled with, Xn is filled with 1, 2.15, and so on, right? Now I get Un plus 1, and then something. Then you now use matrix norm instead of, right? You now use matrix norm instead of vector norm, right? So you can use 2 norm, 1 norm, infinity norm, any norm, right? That's an absolute. I just chose 2 as an example, but you may use infinity norm more. So this is the reason why we learned about norms. Check whether the solution is close enough to the previous one. So we are generating many matrices or vectors, right? So generate this matrix or vector, generate this matrix or vector, and so on. Yes? They should not be handled individually. They should be handled as vector or matrix. In other words, Xn matrix or vector, and the next one, Xn plus 1, should be handled as one object, one entity, minus another entity. And then that difference, now matrix norm or vector norm, should be small to quit, right? To stop loop. To stop the loop, the difference of quantity, right, difference of matrix or vector should be small enough. Because if there is some kind of huge change in matrix or vector, it means we may need to run more loops to better the result. So not individual thing difference. Yes? Up this mean, you mean? Up this mean? So we are solving a system of 9 unknowns. 9 unknowns happen to have array style, right, naming, right? Array style naming. But it's possible to use x1 through x9 if you don't like it, right? Or ABCD is okay. You don't even have to use array. The key idea is not whether it's an array or something. Key idea is solving a system using SOR. SOR means we should have initialization, and then after initialization, we run the loop many times to get the better result, especially convergent result. Then how do we know when to stop? When the previous result and the next result do not have big differences, then you stop. Then how do you measure it? Either matrix norm or vector norm. Mm-hmm. So in the summary, you can find the idea. So in the summary, this is the weight W, right? This is W that you can use with n equal to, in this case, 4, right? N is equal to 4. There are 4 subuniverses. So theoretically, people found appropriate W that we can use. For instance, if it is 4, how large is this? So let's open MATLAB and then calculate. Excuse me? I see. Thank you. Is this the place? Is this the place? Confusing, right? This could be the place. So, I don't know whether this is correct or not, but you know how to calculate W. So assume that you subdivide, you somehow divide by many subuniverse and happen to have like 10 different subuniverse, then you should be n equal to 10. So assume that n is equal to 10, then what happens? Let's change n. Then W should be 1.5. So depending on n, we have different W. So please check the problem from beginning to end and check whether, let me know whether you can completely follow these steps to accomplish the goal or you have some difficulties. No more questions? Great. Then we will cover interpolation. And interpolation idea was finding a function passing through the given set of points. Why do we care about these things? The reason was data representation. If we store the curve information using the curve itself, then at least we need, for instance, even in this curve, we need 100 or more than 100 point information. But it's waste of storage. And assume that we magnify, then pixelation problem happens. But if we use interpolation, instead of storing this curve using 100 different points, we can store the data at the given points. Then 5 points determine the curve itself. In other words, I want to store the curve how? By storing the first data point like 1, 5, and the second data point 2, 6, third one 3, 5, fourth one 4, 6, and then 5, 4, right? So this is the curve. This is the curve. So sometimes when laser printer malfunctions, instead of printing out the one that we want to get, they print bunch of numbers like these. Because numbers are stored very efficiently, even a small file can cost like 200 pages, a bunch of numbers. Why? because somehow the translator converting these things to curve is broken, then it is treated as text. Then text, like these are treated as text, then just printing out a bunch of numbers, page after page after page, it prints out. Have you seen these things before? I saw this in some inkjet printers. Why? Because some converter converting these things into actual thing is broken. Any questions? So this is the reason why we are studying interpolation. So believe it or not, even today, you somehow saw the application of interpolation when you watch TV or use cell phone. Your voice is recorded this way, then transmitted. In any case, we are doing interpolation and we are doing very basic theory. Basic theory is storing, instead of even storing, find these kind of function once points are given. Once a set of points are given, can you find the functions? And we learned about Vandermonde idea, right? Vandermonde, Lagrange idea, Newton's idea. I even programmed Newton. But there is some bad phenomenon. If we have too many points, then high order polynomial behaves like oscillation, called Longer-Murray phenomenon. Because of this problem, we do not use high order, high degree polynomial, but we instead use something called the spline. And spline should satisfy the matching condition, right? You should pass through the given matching condition plus derivative condition. In other words, the slope from this direction and the slope from this direction should match, but in this case it doesn't match. The slope condition should match, right? Slope condition should match. So we have matching point condition, matching first derivative, matching second derivative condition, all these are there. Then how can you find the spline satisfying that kind of condition? So people developed the method, and the method is finding the second derivative at the given nodes, right? So at the given nodes, find the second derivative, say M1, M2, second derivative, right? The second derivatives are unknowns, and we determine the second derivative using the given system, right? By solving the given system, we determine, and then we, using this second derivative result, we assemble splines. Any questions? So this was covered. And there is one thing that we can control. One thing that we can control is two free variable, M0 and Mn. These are free. So these are not determined. So we may set these things equal to 0. Then it's called natural boundary. And we may replace these things with clamped boundary, right? Derivative. Or some other approach is possible. So if you are interested in this freedom portion, then you may ask me, and then I can let you know what kind of things were done and what kind of room is there to improve supply. But essentially, this is it. This is it for the supply. Any questions? So we covered everything up to this point, and today we will cover very, very important things. So unless you have a question, I will open the note summary part. But if you have a question, ask. So as you can see, these are the things. Then take a look. The case that we covered is natural boundary conditions cubic spline, right? And another case is using derivatives of the spline. Somehow we know the slopes at two endpoints. Then we can insert the condition and then create this clamped spline, right? So these two cases were covered. And what else is possible? One more thing is called, this is the one that I explained, but one more condition is called B-spline. These splines are already created spline. In other words, we don't have to really create spline each time, but B-spline is already there. Then we can just determine the coefficient. We can just determine the coefficient because this spline is already there. B-spline is already created. No matter what, B-spline is already created. Then only thing that we need to do is the determination of this thing. So I will give you an example. So assume that you have first function like this, right? This is B0 function. And assume that you have B3 function. Then by mixing these things, we can create many different curves. Assume that B0 times 1 plus B3 times 1 is the one that you want to express. Then what curve would you get? You would get this kind of curve, right? Do you follow me? Assume that you change this number to -1. Assume that you change this number to -1. I will use new line. Then what happens? Instead of getting this curve, we get this curve. So I just used B1, B0 and B3. But what if we use everything? B0, B1, B2, everything. B0, B1, then we can represent many different shapes, right? So this is the idea of B-spline. So it's like assembling a house using all those things that we already made. So you assemble the house instead of really build the house. So these things are already created. These things are already made. And then using appropriate coefficients, we assemble splines. So this is the idea of B-spline. And this is fully developed area. But in this course, we don't have time to fully cover these things, but giving you the idea is the goal. And the determination of the coefficient is done by, this determination is done by system solving, right? We have system like this, and we can solve this system for alpha vector. And alpha is determined then by alpha, we can assemble the solution in the end, right? In the end, we will get this kind of assembled solution, right? So this is the solution in this case. So this line is used very much. Any questions? I don't ask any problems on this spline itself, but the idea is the same. In the previous case, to determine a spline, we need to know these m values, right? We need to know these m values. These m values determine spline. But now, instead of determining or solving a system to determine m and then assemble later, we use ready-made, right? Ready-made these things, right? So built-in splines are used to assemble later. The only difficulty is the determination of this coefficient, right? Determination of this coefficient. How? We solve a system like this, right? We solve a system like this, and then determine alpha by solving systems. The system solving is so important. After solving this system, determine alpha. Then after determining alpha, we return back and then assemble, right? If 1, 1 is the alpha vector, then we 1, negative 1 is, then we assemble this. So this is it for the V-spline. Any questions? Do you completely follow me? Or you don't have any clue? I don't know whether you know or not. If you don't, then let me know. Then I can visit the place that you have difficulty. You know? Great. Then the next thing is a very, very important thing called transform. So generally, FFT is the abbreviation, fast. This is Fourier. That's Fourier transform. Why is this important? Because it significantly reduces the amount of storage space, very significantly. In addition to that, when you restore, it is very nice. It has very nice quality. Not just that, it somehow decomposes components. For instance, gun sound is different from human voice. Human voice is different from piano sound. Piano sound is different from violin sound. It completely decomposes everything part by part, like spectrum. From young age, I really wanted to know how to read spectrum of light, sunlight or something. I don't know yet. Some friends of mine in chemistry departments use spectrum all the time. I don't know. I don't have any clue. I really want to learn. But I know this spectrum. The idea is the same, but I was not trained in real spectrum reading, light, sunlight, or some kind of light spectrum reading. So the idea is this. Assume that this is the signal or sound recorded, right? In this pattern, if you want to somehow record it, and recording is nice, then we may need to break up these things into many points, right? First point, second point, third point, fourth point, all recorded, right? Then storage space requires like 1,000 points or 10,000 points. Then after storing these things, we will somehow restore the data by using the point, but already some kind of loss is happening. So instead of doing this, what Fourier considered was this one. Everything, not just everything, a little bit vague, right? He thought many things can be written in terms of sine and cosine functions. He considered the sine function of nx can represent almost everything, right? So sine nx, some of these things can represent everything. In other words, the first part, this could be sine 4x times 3 plus 6 times sine 10x plus 0.2 times sine 20x. This could be written this way. So this is his belief. Initially, people regarded this idea very stupid. But later, people realized the value of his idea. Assume that this is the case, then storing the data this way is very inefficient. Why? if we somehow get this kind of data, then this kind of storage might be enough. 3, 4, 6, 10, 0.2, 20. This can store the data and completely recover the data. Do you follow me or not? So you should change your idea completely here. If we somehow want to store the data and we refine it very well, then we somehow sampled 10,000 points, right? Then it may sound very nice, but problem is the storage. A mathematician came and then just stored 6 points. Later, run it. After stress test, after somehow sampling these things at very, very small seconds, right? We can see the gap in the first storage of 10,000 points. But this one, no matter what you use, no matter how you sample, it is perfect all the time. Do you get the idea or not? This is the crux of FFT. So this is used all the time. When ABC or CBS broadcast, they send these things to your device. And your device translates this into this one. Now function is there. Then at each point we can find appropriate height, appropriate volume, depth, everything. So this is already used. And you should have clear idea in your mind. We are not storing real heights or point information. We are storing this kind of information. I'll pause and you may check and ask questions. If you don't, then I will continue. And then, so once you understand the idea itself, afterwards, it's bookkeeping work. It's not very tough. But if you don't understand the idea, even after formula after formula, you don't have any clue what is going on. Then how do we analyze the crime sound? Assume that crime happened and you have somehow sound recording. Then you check all possible sine or cosine n, right? So sine 1x, cosine 1x may have some coefficient, right? May have 0.5, 0.2, right? And then 0.6 with sine 2x, right? 0.8 with cosine 2x. So we completely analyze the spectrum. Then, as you can see, there are not many numbers happening here. Voice might be involved in this portion. Gun sound might be involved in this portion, right? In other words, if you want to turn off the gun sound, then you make this equal to 0, right? And then play. Then you don't hear any gun sound. If you don't want to hear human voice sound, then you turn this off and play. Or if you want to play just gun sound, then turn off all others but this one. Then you hear the gun. This is really helpful. So this is the key idea of the device people sell to make money. After taking math courses, they want to make money. Did this and made device and made money. Really. You completely follow me? So these are called the spectrum. So instead of storing the actual height so this is x direction, right? X direction is like 0, 0.01, and so on, right? So x direction is there. Height is, for instance, 2, 2.7, 3.2, and then 3, and then 2.6 something. So instead of storing these kind of numbers, we are storing 0.5, 0.2 pair, right? And then 0.6, 0.8 pair, and some pair, right? And 5, something, right? So these are stored. Are these heights or related to heights? No. This has nothing to do with height. These are called spectra. So this is the data, right? This is the data, and this is the spectrum. So data creates spectrum, and spectrum restores data by just assembling it, right? Done. So you completely understand the theory after this. Someone who missed this class may come to my office frequently and ask about these things. Then I should completely re-explain this. But in any case, once you completely understand this idea, this is the crux of all those things. Some people are good at formula and present formula but don't know the meaning at all. Some people regard this as height. Oh, height is 5 and 2. No, it has nothing to do with height. So please check all these things and ask questions. If you don't, then I will give you the actual formula. Actual formula is not. The idea is everything. No problem? Then take a look. Assume that you want to filter. Initially, piano sound should be very nice, right? Piano wave should be very nice, right? But somehow, noise is there. Especially old record may have this kind of noise, right? So these are the sound that we hear. A lot of noise. Then we create the spectrum of these things. Then, oh, this is about sine 5x curve with appropriate magnitude like 3, and then a little bit height came from 6 times sine 10x. Somehow this is the dominating one, and then small one, 0.2 times sine 200x. This is noise part. Then in your spectrum, you have 3 at the 5 frequency, right? 3 at the 5 frequency, 6 at the 10 frequency, and then 0.2 at the 200 frequency, right? Then you see the spectrum, 3. So you just sketch the spectrum. 0, 1, 2, up to 200 frequency. And then here, 3, right? At 5, we have 3, right? At 10, we have 6. And then at 200, we have 0.2. So you see the spectrum. Then if you want to remove the noise, you may turn this off and hear the sound. Then it's gone, then great. So this is the method people remaster old, great wood. So this is the way people do it. Not just this, what about compression? If you were to compress the file size, then you don't have to keep a lot of values. Only these Or you may include this, right? Only these 3 pairs are enough, right? These 3 pairs are enough to store. Then you compress the sound very much, right? By just these 6 quantities, 6 numbers. The compression is possible. So please browse the idea part and let me know. Any questions? Then now, one twist. People do not want to handle cosine and sine separately. Handling these separately means some kind of inconvenience. So people decide to use complex exponential function. Instead of separating these things, we can call this e to the power of I theta, in theta. So this is a theoretical twist. Not practically different, but theoretically it is twisted this way. Then, in the past, we did this kind of thing. Oh, a n cosine n theta sum, and then b n sine n theta sum. So we need to store a n and b n. But with this thing, we can just store c n e to the power of I n theta, where c n is a complex number. But in this sense, we lost the goal. Theoretically, we can use just one character Cn. But Cn should be stored as complex numbers, and complex numbers require 2 real parts. So theoretically, we saved space, but practically, we return back to the same situation. You follow me or not? Complex numbers are used to mix sine and cosine together in one function. So I don't have much time to explain the full complex variable thing, but roughly this is the idea. Assume that you have 4 plus 4 cosine theta plus 2 sine theta. Then, I will use different number here. 3 theta and 5 theta, right? Assume that you have this function. Then somehow you can represent these things using e to the power of I 3 theta, right? 3i theta, and then e to the power of 5i theta with appropriate C3 plus C5, which are complex coefficients. It's possible to do it. But here, C3 and C5 are complex numbers. So we lost the advantage. Instead of using 4 and 2, we decide to mix those things in 2 functions, right? In one complex function, but we need more complex numbers, right? So we need more spaces. Somehow we lost the goal. But in any case, this is the one that we use. In other words, any f can be written theoretically, right? Fourier idea was sine nx cosine nx combination, right? So this is Fourier's idea. But now in theory, current development or modern development, people use e to the power of in x, right? E to the power of in x to approximate the function. Then you may think, wow, it's way more convenient, but it's not. As you can see, complex coefficients are involved. So when you see the spectrum, you will see real part spectrum and then imaginary part spectrum. Two parts are separately represented. For instance, somehow coefficients for frequency, one is 1 plus 2i, frequency, right? Frequency for 2 is 3 plus 5i, and frequency for 3 is 6 minus 2i. Instead of storing these things as complex numbers, people create the spectrum for real part. 1, 3, 6, right? 1, 3, 6. And then imaginary part, 2, 5, negative 2. 2, 5, negative 2. So we create two spectrums covering individual spectrum of real part and imaginary. Please browse the idea and ask questions. Do you follow me? You now clearly know why two different real and imaginary spectrums are required, right? Because we somehow try to combine sine or cosine function using e to the I and x. Then automatically complex coefficients happen. Because of the complex coefficients, we now need to represent these things in real and imaginary by separate. So you should not ignore either imaginary or real spectrum part. Anything that has huge value might be important in the representation of the function. Function is somehow analyzed, right? Analyzed by sine, cosine, or generally e to the power of I n x. Then final piece of the puzzle is the actual formula. It's very straightforward. Take a look. F is given, right? F is given. Then the data F multiplied by e to the power of I omega x is integrated, gives us spectrum. Once spectrum is given, then we do the reverse thing to restore the data. So all the steps are in just one formula. Theoretically, just one set of formula, right? One set of two formulas. But now we create the discrete version of this integration. Discrete version of this integration is the sum version, right? Sum version replaces integral version. And then we have the same thing. Take a look. A0 up to an minus 1 is the signal. Voice, right? Volume or height, right? Some kind of pitch. So this is the signal. Then by using this signal, right? By using this signal, we generate spectrum, right? By using these things, we generate spectrum. This, right? Data height, right? Height. So like voice, right? Or piano sound. Then by using this signal, we generate spectrum. Right? These are used here to create this spectrum. Once spectrum is created, we store these things on CD. Then CD player reads the spectrum and then restore data using this thing. Then we can generate this. But we are not just keeping all these numbers. When you see these numbers, we will see noise or unnecessary portion. Assume that we want to do compression and we want to just use 10% of the storage place necessary compared to the full recording. Then we drop many unnecessary portion, store a few things. Usually there is some kind of device. I don't know, is it synthesized? I do not know the device name, but some kind of thing. And then they have a lot of keys. So they check, they somehow check and then reduce that part and then check noise goes or actual thing goes. So in some sense, human recognize the difference, but machine just create spectrum but do not analyze machine itself. Of course, if you can make that kind of machine, your machine might be more expensive, right? In any case, data creates spectrum, right? Data creates spectrum, right? Data, some creates spectrum. Then spectrum is stored and sent or somehow broadcasted. Then the receiver receives the spectrum and then restore the data. And then we can hear the signal, sound, everything. This is it. So believe it or not, you used these things from young age. You took advantage of these things from early age. The only thing that you didn't do was learning the theory. But now you learn the theory. So like next time I finish it and then go to the next chapter. Let's stop here.